All right, Chapter 10, aqueous solutions. We talked about some solubility stuff last time, but we were talking about it in terms of a qualitative approach, whether it dissolves or not. We'll be covering a little bit more of a quantitative approach, so using some actual numbers and talking about the degree to which something is soluble rather than just it is or it is not. So solubility of a compound is defined as the amount of compound, typically in grams, that dissolves in a certain amount, usually milliliters or grams or liters of a liquid, a solvent. For example, the solubility of sodium chloride at 25 degrees Celsius in water is 36 grams per 100 grams of water. So in 100 milliliters, 100 grams, you can get 36 grams of sodium chloride into solution. If you get up to that amount, then that is what we would call a saturated solution. You cannot get any more salt to go into solution. So the solubility limit is saturated if you're at that amount. When you have a saturated solution, you've got the maximum amount of solute, the thing that you're dissolving in the solvent, under those given conditions. If you add additional solute, assuming the solute is a solid, it will not dissolve. And when it's a solid, the part that I mean about when it's a solid, it'll stay as a powder or whatever material, whatever shape that it was in before at the bottom. So extra salt will remain undissolved at the bottom of the container. And no matter how long you stir it, no matter how long you leave it with an automatic stir bar or whatever, or you shake it, it will not dissolve. It's not going to go into solution. Which is somewhat convenient because you can prove to yourself that you have a saturated solution if you have extra undissolved material at the bottom of your container, which is common for saturated salt solutions, saturated sodium chloride solutions that you'd often have on hand in an organic chemistry lab. An unsaturated solution, on the other hand, is not saturated. It's less than saturated. This is typically the solutions that we are dealing with. Has not reached the full total amount that you can dissolve into that amount of solvent. So you can add more. There's also another term for solutions that's a supersaturated solution. Supersaturated solution goes above and beyond the normal saturation limit. And you might think to yourself, how is that possible? We just said that saturation is the limit. You can't go over the limit. And the key is that we would be changing our conditions. So it's actually pretty easy to make a supersaturated solution. You just have to change the conditions. So normally if you have a supersaturated solution, the solute, the dissolved material, the dissolved chemical, will precipitate, it'll form a solid out of the supersaturated solution. An example of a supersaturated solution that we're probably very familiar with is a can of soda. A can of soda, assuming it's carbonated, is pressurized around 2 atmospheres of CO2. So when you open it, that really satisfying whooshing sound and the click of the can opening, that's the sound of that CO2 being released, and then it bubbles a ton, because it's a supersaturated solution, we've got extra carbon dioxide dissolved into our liquid, into our soda, and so that's going to immediately start to bubble out. This is especially evident if you have a warm can of soda or a warm bottle of soda. If you have a really cold can of soda, you might notice sometimes really cold cans of soda, like freezing temperature cans of soda, if you give them a little bit of a squeeze, they're not quite as firm because of the decreased temperature decreasing the pressure. There are some examples of supersaturated solutions in the slides here that you're welcome to reference. One of them, I believe, is showing ammonium nitrate crystal formation. Those are pretty cool because you can get a supersaturated solution and it's perfectly clear, assuming that you've got nice glassware, clean glassware. And then if you touch the surface with like a glass stir rod or something, or you go and scratch the bottom, then crystals will start to appear either somewhat slowly, or in extreme cases, you touch it and it immediately forms these spikes of sodium acetate or ammonium nitrate or other types of crystals. So there's things that affect solubility. Temperature is one thing that affects solubility. If you've ever tried making sweet iced tea and you cool down your tea before you try to add the sugar, you will know that solubility is affected by temperature. It takes forever to get sugar to go into cold tea. Getting it to go into hot tea, super easy. Generally, the solubility of solids increases with increasing temperature. So as you increase the temperature, the hotter the liquid is, more easily the solid will go into solution. So sugar dissolves much more easily in hot tea than in iced tea. So usually if you're making your iced tea ahead of time, you'll add sugar in before you cool it down. You'll make it hot, you'll add your sugar in, and then you cool it down so that you don't have to wait forever for it to go into solution. The temperature dependence of solubility varies, as shown by this solubility curve chart. So on this graph, we've got temperature on the x-axis, so left to right we're increasing temperature. On the y-axis, we've got grams of solute per 100 grams of H2O. So this would be a measure of our solubility. Low is low solubility, high is high solubility. So we can see generally that the trend for all of these different colored lines, not all of them, but many of them, as we move left to right, they also move up. And that's for not all of these. Some of them actually decrease. The general trend overall, though, is that if we increase the temperature, we will also increase the solubility. This is another time when I like to make this one-dimensional graph of the amount of energy. In this case, I usually do temperature. Temperature and energy are related. Of our three states of matter, what's our lowest energy state of matter? What's our coldest state of matter? Solid. What's our mediumest state of matter? Liquid. And more energy than that is gas. So if we have a solid that we're trying to dissolve into a liquid, how can we make the solid more like a liquid? What can we do with temperature to make it more like a liquid? Can we increase the temperature or decrease the temperature? If we increase the temperature, it makes our solid more like a liquid. Increasing the temperature makes the solid more like a liquid, and that increases solubility. And you might be thinking to yourself, well, this isn't really that helpful because I already know that solids dissolve better into hot water versus cold water. Why do we need to know this? And I'll show you that once we get to gases, because gases also have solubility in water. A common way to repurify or purify solids, if they form nice crystals, is recrystallization. This is what we're doing in our alum lab. This is what we're waiting 2 weeks to find out about, is recrystallization. So you take a saturated solution of the solid, you prepare that at an elevated temperature. Or in the case of our lab, we probably heated it up past the temperature and if we weren't saturated at that temperature. It doesn't really matter because we raise the temperature quite a bit for most of our solutions. As the solution cools down, the solubility decreases. And if you do that slow enough, or if it can crystallize fast enough, then you'll get really nice crystals that come out of solution. So you'll form crystals as it comes out, and the crystalline structure tends to reject impurities. So crystals tend to reject other chemicals if we're making crystals that are just one type of chemical. So our alum crystals, the alum crystals have a strong affinity for each other. The alum molecules have a strong affinity for each other, the salts or whatever they are. And so they'll tend to form crystals with only the other alum particles. And when they do that, it'll push out the other impurities. It's sort of like when you mix water and oil together and you shake them up. The water really has a strong affinity for itself, and so it pushes all of the oil out. It says, no, you can't hang out with this oil, get out of here. And crystals also do the same thing, if you give them enough time to exclude those impurities. The other thing that we're doing in our alum lab is we're letting it sit out for a long time, and so some of that water is evaporating, and so we're reducing the amount of solvent that we have in our solution, and that's also going to cause our solubility of the solution to go up as we're removing some of the liquid. And by solubility, I mean like the amount that we have dissolved for the amount of water that we have. So that's going to cause our crystallization to proceed as well. You can do recrystallization at home by making rock candy. This is something that is safe to do, assuming that you use sugar that you have at home that is presumably not bad, and you don't use dirty glassware. So in order to make rock candy at home, you want to prepare a saturated sucrose, table sugar solution at an elevated temperature. So take some water, heat it up, add a bunch of sugar until no more sugar will dissolve, pour off that super syrup that you make, and if you have an extra insulated cup or something, you can put it into that. That will prevent it from cooling down as quickly. And then you can dangle a string like from a popsicle stick or something, or a really long toothpick or a kebab skewer or something. Dangle the string, or if you've got little sticks or something, leave that in there to cool and sit for a while. Oftentimes recrystallization takes a long time, and if you interrupt it, sometimes just like you move it a little too much and then it's like, no, we're done. I don't know why that is. As you cool it down, you should start to see crystals forming on your string because your string or your whatever stick you're making these on has some rough spots. That makes for good sites for these crystals to start to grow. And if you wanted to, you could probably also add food coloring, you could probably add flavoring, and make your own very fun rock candy and see how big your sugar crystals can get. If you do this, please send me pictures. All right, so that's an example of something that you can do at home, unlike taking a bath with a toaster, which you cannot do at home. Don't do that. Okay, so that's solubility of solids. Solutions of gases in water are things like soda or anything else that's carbonated. Most liquids that are exposed to air are going to contain some dissolved gases. If you've gotten well water, oftentimes well water is kind of gassy when you get it. And if you give it a good shake, that'll help get some of those extra gases out. It's crucial, it's critical, it's important to life on Earth that gases are soluble in liquids. So lake water and seawater contain dissolved oxygen that is necessary for fish to survive. Fish also need oxygen to live. So if you don't give your fish oxygen, if you don't have a pump in there that's recirculating the water, it's got the little waterfall thing going on, there's a good chance that your fish are going to run out of oxygen, or they'll have to go up to the surface to go get that oxygen. Our blood also contains dissolved nitrogen, oxygen, carbon dioxide, and some other things, and our tap water also has some dissolved gases in it. The solubility of gases in water is the opposite of what it is for solids. So we've got the same sort of graph here. We've got temperature on the x-axis increasing left to right. We've got solubility on the y-axis increasing down to up. And generally, you'll notice that as we travel left to right, we're seeing these curves coming down. That means that as we're increasing temperature, our solubility is decreasing. So solubility of gases in liquids tends to decrease with increasing temperature. An example of this is warm soda is going to fizz more than cold soda. And that's because the solubility of the dissolved CO2 decreases with increasing temperature. They have the same amount of CO2 dissolved in them. If it's hotter, more of that is going to be able to come out. It's more supersaturated because it's hotter. Let's look at that one-axis graph that I've drawn now. This would be my fourth time, I think. We've got three states of matter. Temperature is our one axis. Temperature also could be energy instead. We've got our solid, liquid, and gas. What do we need to do to a gas to make it more like a liquid in terms of temperature? If we decrease the temperature, that will make gases more like a liquid. And solubility increases. I really like this as a way of remembering how solubility trends work. You can also just remember that gases have the opposite solubility trends for solids. So if you decrease temperature, you increase solubility. If you increase temperature, you decrease solubility. There's an example of increasing temperature and decreasing solubility that you may be familiar with. I think it's on a slide, but if it's not, then remind me. Solubility of gases also depends on pressure. And we've got Henry's law that describes this phenomenon. So the higher the pressure of a gas above a liquid, it's like CO2 in a can of soda, the more soluble the gas is in the liquid. The way that we might explain this is high pressure forces more gas into solution. High pressure forces more gas into solution. At some point, some of those gas particles, those gas molecules, are going to say, we've had enough of this high pressure nonsense. We're just going to go hang out with the liquid. And so they get driven into solution. A can of soda is pressurized with CO2, carbon dioxide. When you open that can of soda, you're releasing that pressure. Again, it's like around 2 atmospheres, if I'm remembering correctly. Because we've released the pressure, we've lowered the atmospheric pressure from 2 atmospheres to 1 atmosphere. For Henry's law, the higher the pressure of a gas, the more soluble the gas. The opposite would also be true. The lower the pressure of the gas, the less soluble the gas is in the liquid. So we lower the pressure, that's also going to lower the solubility. Now we've got a supersaturated solution of CO2. So supersaturated CO2 causes that rapid fizzing that you get when you open a can of soda for the first time. Any questions about solubility so far? I don't remember if it shows up later in these slides. The place where you would have seen the relationship between temperature and solubility is if you've ever boiled water. If you've ever boiled water and you're standing there watching water, waiting for it to boil, right before it starts to boil, you see little bubbles coming up. And you see those little bubbles coming up and you're like, all right, it's game time, we're boiling. And then you wait another 5 minutes and then it actually starts boiling. Those little bubbles that you see before, those are dissolved gases leaving the solution. That's not its actual boiling. That's why they're really small bubbles compared to the big bubbles that you often get with boiling. So as you're increasing that temperature, you're decreasing the solubility of the gases, and so you're causing all those dissolved gases to leave. So it's actually a false warning. Like, it does let you know you're getting close to boiling, but I've been fooled many times by thinking that it was boiling, and then disappointedly my pasta takes forever to cook because it wasn't actually boiling. There are some ways that we can specify solution concentration. One of them was solubility, so the amount of grams of solute or solid that we could dissolve in a certain amount of liquid. We can also do mass percent, which is the number of grams of solute per 100 grams of solution. Sometimes it's more convenient to use different units. So a solution with a concentration of 14% by mass contains that percentage number per 100 grams. So change the percent to grams. Per 100 grams solution. So the solution is both the solvent, the liquid, and the solute. Solution is solvent, what we would normally think of as liquid, and solute, the thing that we dissolve in it, or the minority component. However many solutes there might be in there. This is helpful because we often don't know exactly how much solvent we have in a specific amount of a mixture, because when you add a solvent and a solute together, your volume increases a little bit because that solute has to go somewhere. So you can't just measure the volume and say, well, I've got this exact amount of solvent in here. So it can be really tricky to measure just the amount of solvent. That's why we're doing 100 grams of solution. Let's say that we have a salt solution. It contains 12.8 grams of sodium chloride, NaCl, and 357.1 milliliters of water. Assume that the density of water is 1 gram per milliliter, which is generally a safe assumption to make. In most circumstances, the density of water is 1 gram per milliliter, most that we encounter at least. So if we want to calculate mass percent, our formula for mass percent is grams solute over grams solution times 100%. This is similar to the mass percent that we've used before. Just instead of the whole thing on the bottom, we're now calling it solution because we're working with a liquid. So the couple of things we need to do, we need to identify our solute. What's our solute in this case? Yep, it's 12.8 grams sodium chloride. And on the bottom, our grams of solution. Our grams of solution is going to be our grams of sodium chloride plus are 357.1 grams of water. When you add them together, the masses add up, nothing disappears. Sometimes people think mistakenly that the solute doesn't have mass anymore once you put it into solution. That's not the case. It still has mass. Law of conservation of mass tells us that. And then we're going to multiply that by 100%. Please note that if you do this on your calculator, you do need parentheses on the bottom. Otherwise, you'll get a freaky answer. Like 35,711, I think is what you get if you put it in wrong. And in this case, the number that comes out, 3.46%. And you could give it units of sodium chloride or sodium chloride and H2O in water. Questions? Great. There are some other commonly used units. So percent is parts per 100. The amount, the parts just means the amount per 100 of whatever the same amount is. So grams per 100 grams is parts per 100. How many pennies are in a dollar? I know at least one of you knows this. How many pennies are in a dollar? Somebody say something. Are we scared that we're wrong about the currency that we use? Not as young as I used to be. 100, thank you. Yes, there's 100. And what's the other thing that we can call a penny? A cent. Per cent literally just means per 100. So parts per 100 is the same as percent. It's exactly the same, it's just different words for the same thing. Other units that you'll commonly see, there's also parts per thousand or per mille, per M-I-L-L-E, I believe is how it's spelled. That's not on here. There's also parts per million and parts per billion. Parts per million, parts per billion, you'll often see, like if you look at a water quality report or if you're looking at the amount of pesticide residue that's on your fruit and vegetables or the maximum allowable limits for those sorts of things. That's typically where you're going to see parts per million, parts per billion, and even possibly parts per trillion. Those will also be like contaminant numbers, like we've got a certain amount of particulate matter in our air quality that might also be represented in parts per million, parts per billion. So parts per million, grams per 1 million grams solution, for example. You could also represent it as something that's a millionth of a gram, so you could represent it as micrograms per gram, nanograms per milliliter or milligram, stuff like that. It's not super important. We won't really be testing you on that in this class. If you want to use mass percent in calculations, we can do that. We've already learned how to do that actually. So shouldn't be any surprises there. It's a convenient way of converting between the mass of the solute, which is on the top, and the mass of the solution, which we'd represent as 100 grams on the bottom. So for example, you can rewrite 34% as 34 grams solute, and since percent means per 100 grams of solution. How much sucrose, sugar, in grams is contained in 355 milliliters, 12 ounces, of a soft drink containing 11.5% sucrose? Assume a density that's not 1, it's 1.04 grams per milliliter, because it's not just water, it's got other stuff in it. So the first thing that we want to do is we want to identify we're working with 11.5% sucrose. That means that 11.5% sucrose in water. 11.5% equals 11.5 grams sucrose per 100 grams solution. In this case, our solution is the soda, the pop, if you will. And that's the conversion factor that we're going to use. So let me turn this into an arrow instead of an equals. So that's how we want to change from mass percent to a useful conversion factor. We are going to assume a density of 1.04 grams per milliliter, so 355 milliliters. And then we have to figure out, are we going to multiply or divide by density? Let's look at what happens if we divide by density. If we divide by density, we put 1.04 and grams on the bottom, and milliliters goes on top. Do any units cancel out if we do it this way? No, units don't cancel out, so this is the wrong way to do it. This is why we check before we just plug stuff into a calculator. Until you're very confident that you're doing these things correctly, it's always a good idea to go ahead and just write them out. So we're going to do the opposite. We're going to multiply because the units tell us so. So now our milliliters will cancel and we'll end up with grams. So 355 times 1.04, 369.2 grams soda. Now what do we do? Our goal is to find the amount of sucrose. Our mass percent that we just transformed into a conversion factor has sucrose in it. It also has soda in it. We have grams of soda. Grams of soda is on the bottom in our conversion factor. So if we multiply by 11.5 grams sucrose over 100 grams soda, the grams soda cancel, we're left with grams of sucrose. So times 11.5 divided by 100. So in our soda, there is 42.5 grams of sugar, which is a lot of grams of sugar. Questions about that calculation? The other thing that you could do is what I do. Turn that percent into a fraction, 0.115 grams sucrose over 1 gram solution or soda. It's the same as the 11.5 grams over 100 grams. We've just done the division already. So it's a little bit quicker. It's fewer things to put into your calculator. You can do either one. They're mathematically identical. You'll get the same answer both times. Another way that we can specify solution concentration is molarity, and we have seen molarity before. Molarity has units of capital M. So we've seen, for example, 3M, I forget what the solution was, I think it was hydrochloric acid, and in our lab yesterday we saw 6M, hydrochloric acid. This is what the M was, molarity. It's important that you write it as a capital M, or in uppercase, the majuscule M. It has to be uppercase, lowercase is something else. It's defined as the moles of solute per liter of solution. So here's our equation for molarity. You'll get it on the exam. It's also important to point out that it's solution. And again, solution is solute plus solvent. Or solutes plus solvent. It's the whole thing, the whole mixture. And again, this is very convenient because liters of solution, if we measure the volume of the thing that we have, that's pretty easy. If we tried to figure out how many liters of water do we have in here, that's a much more difficult question to answer because we've got things dissolved in there that are inflating the volume. And there's probably a way that we can do it, but it would not be fun. So molarity is moles of solute per liter of solution, not per liter of solvent. This is very nice. Any questions about one of the best concentration units, molarity? If you want to make a solution of a specific molarity, you won't have to do this. You won't have to answer questions about how to do this. But in the future, you might have to make solutions. It's very important that you don't fill up to your maximum volume before you add your solute. So here we've got 5 steps. The first step, you measure out the amount of solute that you want to put in. You know how much volume you're going to make. You figured out how many moles you're going to need. So you measure out the grams that you're going to need. So we've got 120 grams. We're going to add this into our volumetric flask. The volumetric flask is a piece of glassware that is useful for measuring exactly one volume. There's only one volume that you can measure with a volumetric flask. That's the only volume that it's good for, but it's really good at measuring that one volume. So this line on the skinny little neck of the flask, that's where we stop. That's our one volume that we can measure with this. You're going to add in your solute with some solution in here. You want the solution to not be going up to where it gets really skinny here, because then it makes it really hard to shake. If it's below that, then you can give it a really nice swirl, or you can give it a little bit more of a vigorous shake, and you'll be able to get your solute to go into solution. If you get it up into the neck, it gets much more difficult for you to shake it up because it's basically full at that point. And then once it's completely dissolved, then you can fill it up exactly to that fill line, and don't go over even a drop. Because if you go over even a drop, then it's no longer that one volume that you're good at measuring. It's a little bit more than that. Sometimes that might be fine, but generally, that's where I've had trouble with making solutions. So I would, as some of my grad school work, have to make up a set of solutions in these sort of flasks, and it would be, I'd have to do that basically 12 or 13 times, all starting from, so I'd do one solution and then I'd make multiple solutions from that. I'd take one of those and I'd make multiple solutions from that, and then I'd take one of those and make multiple solutions from that. And it really sucked because I was making basically exactly the amount that I needed to, and so if I screwed up on making one of them, then I might have to start all over and remake all those solutions. If I went even a little bit over that little line because I needed the volumes to be exactly right, or at least within the like 0.1% tolerance of a volumetric flask. All right, let's do a calculation with molarity. Let's show you how to do it. We want to calculate the molarity of a solution made by putting 22.4 grams HCl into a beaker and diluting to a total volume of 1.56 liters. Molarity is capital M. Capital M, molarity, is moles over liters. One of my favorite tricks with molarity is that anytime that you see that capital M that means molarity, you can directly replace it with moles over liters. These are interchangeable. So secretly, if you see that capital M, that big M, what you're actually looking at is moles over liters. It's not 1 unit, it's actually 2 units. And it's a very good conversion factor for moles and liters. Since it's moles over liters, do we have moles? We'll need moles to calculate molarity. We don't have moles. Do we have liters? We do have liters of solution. That's this 1.56 liters. Can we find moles? Also, yes. We can find moles by taking our 22.4 grams HCl and converting it to moles. We just divide by the molar mass. Which is 36.458. Please note that for some of these problems, probably all the problems, many of the problems, you'll need to be able to calculate a molar mass. If you can't calculate a molar mass, you can't start the problem. I might be nice sometimes and give you the molar mass just to save you a little time and brain power, but we should be able to do this like eating chips. Should be second nature. If the chips are there, we're eating them, right? We can calculate the molar mass. It's that easy. So 22.4 divided by 36.458. 0.6144 ... moles HCl. How many significant figures are we going to round that number to? No. But thank you for guessing. It's a trick question. We're not going to round that number. We're not done with our calculation. I don't normally do tricks, but I thought I would do a trick today. We are going to put this entire number into the moles part of this. Because if we round it early, we could end up with a rounding error. We'll end up with a different answer than we would expect. We'll be off by that tiny little bit. It's possible. Okay, so capital M equals moles over liters, so 0.61440 ... It's going to have 3 significant figures. That number should have 3 significant figures, but we're not going to round it quite yet. Moles HCl over liters of solution, 1.56 liters. So divide 1.56, and this is 0.394 after we round it for 3 sig figs. Molar HCl. Or molar hydrochloric acid. Basically what I'm pointing out here is we shorten molarity to molar when we're reading off the unit. Forgot to put my phone in do not disturb and I'm getting spam text messages. This isn't Jerry, wrong number. Deleted. Questions? Cool. We can also use, as I alluded to previously, molarity in calculations. We can use it as a conversion between the 2 units that make it up. Since capital M equals moles over liters, we can use it to convert between those 2. So as an example, determine grams of sucrose that are contained in 1.95 liters of 0.781 molar sucrose solution. Again, this reads as molar. We drop the itty. When we pronounce it. So the trick, the key, the thing that I think is the easiest, the fastest to do is just go ahead and change that capital M into moles and then put liters on the bottom. So to do that transformation, 0.781 molar transforms magically through the power of algebra into 0.781 moles over 1 liter. We can do that absolutely for free. And now we have a conversion factor. We can, of course, write in the 1 for the liter on the bottom. And so now that molar is moles over 1 liter. Since we have got 2 units, secretly 2 units in there in molar, we're going to start with the other thing, 1.95 liters. And because we've got moles over liters, this tells us that we multiply. We've got liters on the bottom. We want that to cancel out with the liters that we have. So 1.95 liters times 0.781 moles per liter. This will tell us the number of moles of sucrose. 1.52295 moles sucrose or sugar. Does anyone have questions about that part of it? That's my favorite way to do it. I think it's the best way to do it. It's so fast, it's so easy. It requires you to be able to do dimensional analysis, to look at the units and figure out what to do based on the units. Some of you aren't going to like that, and so you might prefer to use molar equals moles over liters, and then rearrange it. That looks an awful lot like a density equation, right? Remember, our density equation is density equals grams over mass over volume. And there was a trick that we could do with density equals mass over volume that some of you probably liked, the little triangle thing. We can do the same thing with molarity. This is the other case that we can use that triangle trick. So if you would like to use the triangle trick instead, you're welcome to do that. As a reminder for the triangle trick, our little pyramid trick, whatever you're trying to find, you cover that thing up. So if we're trying to find liters, for example, we cover up the liters, and we would see the relationship of the other two things. It would be moles over molarity. So if we do moles over molarity, that'll get us liters. We don't have to do any algebra. So that works here because it has the same form as density equals mass over volume. You're welcome to use that as well. Still no questions? Deafening silence. So we'll take our moles and we multiply by 342.297 grams per mole, since that's the molar mass. And in this solution, there would be a whopping 521 grams of sucrose. Now one for you to try how many liters of a 2.25 molar copper sulfate solution, copper 2 sulfate solution, contains 55.8 grams of copper 2 sulfate. I'll give you 2 minutes. Some helps if you need them. What are we finding? We're finding liters. Our question words, how many, and then liters. So we are finding liters. Liters is our goal. We are given two pieces of information. We are given 55.8 grams of copper 2 sulfate. We are also given 2.25 molar copper 2 sulfate. I like to start with the simpler unit. You don't have to, technically, but it just feels nicer to me. Which of these is the simpler unit, grams or molarity? Grams. Grams is 1 unit. Molarity is secretly 2 units in a trench coat. So 55.8 grams CuSO4. What is molarity? How do we find molarity? What's the equation for molarity? Moles over liters, great. So one thing that we can do is we can turn that capital M into moles over liters. This is our trick for getting liters out. This molarity equals moles over liters. So to find liters, we need to solve for liters in our molarity equals moles over liters. This is how some of you might prefer to do it. If we use the little triangle trick, then we would find out that liters equals moles over molarity. And that works. That will solve the problem. We would get that by swapping the liters and moles, multiplying both sides by liters, dividing both sides by molarity. We're doing our little cover up the thing that we want to find with the triangle trick. So in order to find liters, we need moles and molarity. We have one of those. Which one do we have? We have molarity. We were given it in the question, the 2.25 molar. We don't have moles, but we have grams that I forgot to write. G, grams copper 2 sulfate. So we can find moles. We're going to divide by our molar mass so that the units work out. I guess this is also a thing that we could use that triangle trick with. We're not going to think about that for now, though. So this will get us to moles. We need moles. Let's go ahead and just evaluate it, because I'm guessing that's what some of you will do. So 55.8 divided by our molar mass. This is less than a mole, 0.3495 moles CuSO4. We're going to plug that in. We're going to plug our 2.25 in. So liters is going to be equal to 0.3495 ... because there's other stuff and we didn't forget about it. We did use it. We did write it. We promised Mr. K. Don't make us write everything out. Over 2.25 molar CuSO4. And this will equal 0.155, and stop there because we're rounding it for 3 sig figs, liters CuSO4 solution. So if we, for some reason, needed to deliver 55.8 grams of copper 2 sulfate, we would measure out 155 milliliters, and that would get us about right on the money. Questions? Shocking silence. The reported concentration, the concentration that we typically see, is the concentration of the molecular solute, or of the formula units of the solute. If we have the reported concentration of a molecular solute, something that is all nonmetals, that typically reflects the concentration of the solute as it actually exists in solution. If we are doing an ionic solute, that reflects the concentration of the solute before it is dissolved. So the formulae, if you will, of our ionic compound. Why is this relevant? Because we might need to know our ionic concentrations. For example, a 1.0 molar calcium chloride solution. How many calciums do we have in calcium chloride? 1. So 1.0 molar CaCl2, our ratio of calciums to calcium chloride is 1:1. Within every calcium chloride, there's one calcium 2 plus ion that will be produced if it dissolves. And so it's still going to just be a 1.0 molar calcium 2 plus solution, or that would be the concentration of our calcium ion. However, look at our chloride. We have 2 chlorides. So every 1 calcium chloride is going to produce 2 chlorides. So if we do the same little bit of stoichiometry, 1.0 molar CaCl2, that subscript of 2 lets us know we're going to produce 2 Cl minuses per every 1 CaCl2 calcium chloride. Our concentration of chloride is actually 2.0 molar with respect to chloride. For some of you, you will be able to look at the subscript and just, you don't have to write it out, you can just multiply it and you'll get the right answer. Writing it out may be helpful to start. The concentration of individual ions can be approximated from the overall concentration. So again, for calcium and chloride, we'll do it with something that's not 1 molar. We have a 1.25 molar calcium chloride solution. We want to determine the molar concentrations of calcium 2 plus and Cl minus. So we're going to do a little bit of stoichiometry. Our 1.25 molar CaCl2 is our starting point. There are 2 ions that we're calculating for, calcium and chloride. As previously discussed, 1 Ca2 plus per 1 CaCl2. So this is 1.25 molar with respect to the calcium 2 plus ion, assuming it's a strong electrolyte and it completely dissolves. And with our chloride, there are 2 chlorides per every 1 calcium chloride, CaCl2. So it is 2.50 molar. We need to remember to add a trailing 0 to keep 3 significant figures. It's 2.50 molar with respect to the Cl minus ion, again because there's 2 for every 1 calcium chloride, and so the concentration is double. Are there questions about why we're doing this, how we're doing this? All right, solution dilution. Oftentimes it's convenient to dilute a solution. The reason that it's oftentimes convenient to dilute a solution is because we typically store our solutions in concentrated, high concentration forms called stock solutions. Stock solutions live in the stock room, often labeled as the prep room, at least here, it's labeled as the prep room. So it's convenient to store our solutions in really concentrated forms and then just take a small amount and dilute it up to make whatever concentration we want. If we need a lot of really low concentration solution and we just buy it in that amount, we're going to be buying vast quantities of solution and we don't have an infinite amount of room in our prep room. So it's more convenient to buy one smaller bottle and just dilute it out. So that's where solution dilution comes into play. And we have one exact formula, one very particular formula that works for solution dilution. This formula only works for solution dilution. Please do not use this formula for anything other than dilution. Do not use this formula for anything else. 0 other things that you should use this for. Use it only for solution dilution. If you use it for anything else and I catch you using it for anything else, I will mark you wrong even if it's the right answer. This is one of the places instructors often have things that they're very particular about. This is one of those things that I'm very particular about. Our formula looks kind of like Boyle's law, which was P1V1 equals P2V2. Solution dilution, M1V1 equals M2V2. The way that this works, the reason that this works, M is molarity, V is volume, and molarity, remember, is moles over liters, liters being a unit of volume. So if we times L and M, all right, let's rearrange this. Liters times molarity equals moles. And if we are simply diluting our solution, M1 times V1, that tells us the amount of moles that we have. We should have the same amount of moles when we're done diluting it, because we didn't take anything out, we just added more liquid in. It's a bigger, more dilute volume, sort of a density-related kind of topic. So in the second state, we should still have the same number of moles because we, again, didn't take anything out. We didn't do a reaction. We just spread out where it was. There's more volume. So the volume goes up, the molarity goes down. That's the reason that this works for solution dilution. And technically, it doesn't work for anything other than solution dilution. Look, I have it in the slides. The equation M1V1 equals M2V2 applies only to solution dilution, not to stoichiometry. It doesn't work for stoichiometry. The reason that some of you might use it for stoichiometry is if you have a 1-to-1 ratio, it does work for stoichiometry. It will still give you the correct answer. If you don't have a 1-to-1 ratio, you will get it wrong 100% of the time, I guarantee it, if you use M1V1 equals M2V2. As an example, how much 6 molar sodium nitrate solution, what is how much asking for? That's the thing that we need to ask ourselves. How much 6.0 molar nano solution should you use to make 0.442 liters of a 1.2 molar sodium nitrate solution? We've got a molarity of 6.0 molar NaNO3. We've got a volume of 0.442 liters. And we've got another molarity of 1.2 molar sodium nitrate solution. Just like with Boyle's law, Charles' law, Avogadro's law, the combined gas law, the Gay-Lussac law, the big thing that we want to make sure that we do is get our 1s and our 2s paired up correctly. We don't want to get them mixed up. We will get the wrong answer if we get them mixed up. So this is a solution dilution problem, N1V1 equals M2V2. We've got one volume. Which molarity does it go with? Does our volume go with 6 molar or with 1.2 molar? Does it go with 6 molar or 1.2 molar? It goes with the 1.2 molar. That links those two things together. So let's call this V1 and M1. It doesn't matter if they're 1 or 2, just as long as they both have the same number. That would make this 6.0 molar M2. The thing that we don't have is V2. To find V2, we rearrange our solution dilution formula. It's going to be M1 V1 over M2. And we plug in our numbers. So 1.2 molar times 0.442 liters over 6.0 molar. So the amount of solution that we should use, that we should start with to dilute this up to 0.442 liters is 1.2 times 0.442 divided by 6. We would be using 0.0884. We'd round it for 2 sig figs, 0.088 liters of 6.0 molar sodium nitrate. We can check that this makes sense. We're diluting this. We're taking it from a high concentration to a low concentration, meaning that we're diluting it, the volume has to go up. So we need to have a smaller volume of our 6 molar solution. 0.088 liters is smaller than 0.442 liters. Questions? Great. This is kind of how that might look if we were making or doing dilutions. If we want to be very precise, we're going to use volumetric flasks. Again, volumetric flasks are good at measuring exactly one volume, and that's all they're good for. So you would add in the amount of solution. So this would be a weird amount to make because there's not going to be a volumetric flask that's 0.442 liters. If it was 0.5 liters, then that would make a little bit more sense. Let's pretend that it's 0.5 liters just for the sake of being able to use a volumetric flask. So we'd take our 6 molar solution, we would add in the amount that we calculated to our half-liter flask or our 500 ml flask, and then we would fill it up most of the way, give it a little swirl to get it kind of evenly distributed, and then go ahead and fill it up the rest of the way with our distilled water or whatever our solvent was. Once we fill it up right to that mark, now we've got our 1.2 molar solution, and we can use it for whatever else we need to. Part of the reason to have these long skinny necks is if you look at a bunch of volumetric flasks that are all exactly the same size, they'll have the marks at different heights because they make the flask and then they calibrate it after that. All the flasks are slightly different in terms of their shape, even though they're very good at making the same sized flask. But they have to put that line somewhere along the neck wherever it corresponds to that exact volume. So that's why they have a long neck, so they've got more extra plus or minus room, and it also means that you've got a small amount of error that you're going to get if you overshoot it or if you undershoot it. It's not going to change by very much, it's more accurate. Okay, solution stoichiometry. We will often do solutions chemistry. So we'll have aqueous reactants and products, and in those instances it's very convenient to specify amounts of reactants or products in terms of volume, milliliters or liters, and concentration, typically in molarity. It would be very not helpful to say you need to react this many grams of the solute with this many grams of the other solute because they're dissolved in other things, And so disentangling the volume and of the whole thing and the grams of the solute would be very difficult. Solution stoichiometry lets us do this much more easily. Our general solution map for these looks a lot like the stoichiometry that we've done before. Previously, in chemistry, we did grams to moles to grams. Oftentimes, we will be doing volume or liters to moles to liters. So it follows kind of the same principle. Our stoichiometry step is still in the middle, just like it was before. But instead of using molar mass, we're using molarity. So molarity instead of molar mass. Note, though, that we could use molarity as a starting unit or molarity as an ending unit. So we can switch it up a little bit. It just depends on the circumstances that we're working in. So here's an example. What volume in liters of a 0.5 molar sodium sulfate solution, who made these slides, will react with 275 milliliters of 0.25 molar barium chloride to completely precipitate all barium 2+ in the solution given the balanced chemical equation. Very nice to say that it's balanced. We could have figured out that it's balanced. We could have guessed. We've got coefficients. It's probably balanced. What are we finding? Because there's a lot going on here, right? What are we finding? I underlined it. Volume in liters of what? What chemical? Sodium sulfate, which has the formula Na2SO4, which is, of course, not shown here. We're going to change that to I don't remember what this was supposed to be. Whatever, I'll just make the correct one. Not a big deal. Okay, we've got sodium 2 sulfate reacting with barium chloride. That's going to produce barium sulfate and sodium chloride, and we're going to have 2 of those. Great. All right, so we're trying to find sodium sulfate. What's the other thing that we care about? What's the other chemical that we care about? What's the other chemical that's mentioned? Barium chloride, which is BaCl2. So those are the 2 things that we care about. Those are our 2 chemicals. The other things that we're given is we're told that it's a 0.5 molar sodium sulfate solution, and we've got 275 milliliters of that concentration of barium chloride. We have 2 values for one of the 2 chemicals. Which chemical is it? Is it the sodium sulfate or the barium chloride? Two numbers. Which one do we have 2 numbers for? What volume of half molar sodium sulfate? We've got 1 number for sodium sulfate. We don't have everything that we need. We have 275 milliliters and 0.250 molar for barium chloride. We've got 2 things for barium chloride. We can start a problem with 2 things. what I'm going to choose to start with is milliliters. Milliliters is a nice, simple unit. So 275 milliliters. It is actually more convenient to make this 0.275 liters, which is the same as 275 milliliters. We can go from volume to moles using molarity. If we keep in mind that this is 0.250 moles per liter. So magically change that capital M into moles over liters. Alternatively, if we really wanted to, moles equals molarity times volume, or times liters. If we rearrange capital M equals MOL over L, we can also do that. So moles equals molarity times liters. We have liters. If we multiply by molarity, which we are given, this will give us moles of the chemical barium chloride. Do we see how we did that? Do we understand why we did that? If we do not understand how we did that or why we did that, please ask a question. Okay. We have now moles of BaCl2. Our goal, we wrote out liters Na2SO4. We do not have the same chemical, right? BaCl2 and Na2SO4 are not the same chemical. We can convert, we can switch between chemicals with that magical, sometimes hated word, stoichiometry. Stoichiometry just means we're using the ratio, the stoichiometric ratio, the coefficient ratio for the two things. In this case, it's 1 to 1. So for every 1 BaCl2 that we put in, it's going to react with 1 Na2SO4. So now instead of moles of BaCl2, we've got moles of Na2SO4. It's not as important to get the right answer when we've got a 1-to-1 ratio that we do this. We will often not have a 1-to-1 ratio, and so then it becomes extremely important that we remember to do the stoichiometry step. You can't get the right answer if you don't include the stoichiometry. Okay, so now we've got 0.06875 moles Na2SO4. We want to get to liters. We have molarity of Na2SO4. Molarity equals moles over liters. We can rearrange this to find liters. Liters equals moles over molarity. So we take our moles, we divide it by the molarity, 0.500 molar Na2SO4. This will give us liters. So 0.1375 liters Na2SO4. Or 0.138 if we round it, like we ought. We'll take a short break. All right, coming back. A 25 milliliter sample of nitric acid solution requires 35.7 milliliters of 0.1508 molar barium hydroxide to completely react with all of the nitric acid in solution. What is the concentration of the nitric acid solution? So this follows a similar solution map. We're still using the concepts of molarity, and there is some solution stoichiometry. We haven't covered acid-base reactions yet, so I'll give you the balanced chemical equation. So here's our balanced chemical equation. As a reminder, molarity equals moles over liters. I'll give you a couple minutes to answer this question, or work on it at least. All right, to solve this problem, we need to identify the things we're given. We need to identify the thing we are trying to find. We are given that we have 25 milliliters of nitric acid. We've got 35 milliliters of a concentration of barium hydroxide solution. We've got two numbers for barium hydroxide. We're going to be starting with barium hydroxide. The other way we know that we're starting with barium hydroxide is that we were asked to find the concentration of the nitric acid solution, the HNO3. So our goal is to get to molar HNO3. So starting with our simple unit of 35.7 milliliters, we need to convert milliliters to liters. There are 1,000 milliliters in 1 liter. So we're dividing by 1,000. That's going to shift the decimal place over 3 spots to the left. So that gets us from milliliters to liters. With liters, we can take liters and multiply it by molarity. Liters times molarity equals moles. So if we multiply by our molarity, 0.1508 molar, there should be barium hydroxide here to start. If we multiply by our molarity, this will give us the moles. Since molarity is moles over liters, the liters cancel. We now have moles of barium hydroxide. So for those of you keeping track, liters to moles. Our next step, we need to go to moles, but of the chemical that we care about, which is the nitric acid, the HNO3. Our ratio of barium hydroxide to nitric acid is 1 to 2. 1 barium hydroxide equals 2 HNO3. So 2 HNO3 over 1 BaOH2. The barium hydroxides cancel. We're multiplying by 2. And then from moles, we need to go to molarity. So we're switching up the solution map a little bit. Rather than going to liters, we're going to molarity. This is the type of calculation we'll be doing next week in experiment 11 and in our lab practical. To find molarity, molarity equals moles over liters. We have moles of nitric acid. We need to divide by liters. We've got milliliters. Because I like doing everything all in one line, I'm just going to add in, I put that on the wrong side, dividing by liters. So this little chunk is converting milliliters to liters for our nitric acid solution. Another part of the reason that I wanted to include that chunk and put it all in one line is if we look at this full solution map, there's a trick that some of you will be able to employ successfully and others of you should not attempt. We have a 1,000 here on the bottom. We've got a 1,000 here on the top. This is not the part that you should not attempt. We can just cancel those out because we've got 1,000 on top, 1,000 on the bottom. Functionally, what that means is if we've got a volume in milliliters, we started with milliliters, we can actually leave it in milliliters because we have milliliters later. The reason that this works is that milli prefix means 10 to the minus 3. And so if we don't do these conversion steps, the millis stay in there in terms of units. And so we can just cancel the milli prefixes. If you forget that the milli is there, then you might do one of these two conversions and then you will get the wrong answer. So it's fun. I think it's a cool little math trick. Most of you, it's probably not helpful and it's maybe even harmful, so don't do it. But for those of you that like that sort of thing, there you go. So 35.7 times 0.1508 times 2 divided by 25. And the concentration is 0.431 molar HNO3. Questions? You can, of course, if you're doing this problem by yourself, do it in as many steps as you'd like, instead of doing it all in one long stretch, like I like to do it. That sort of conversion is very helpful to do in an acid-base titration, which is what we're going to be doing on Tuesday. What we're going to be doing on Wednesday, our lab practical, is a titration lab. So solution stoichiometry can apply to a titration. Titration is a fancy name for basically just figuring out the concentration of a solution. So in a titration, a substance in a solution of known concentration, that was our barium hydroxide in our example. We know what the concentration is. We can add it to another substance that we don't know the concentration of, but we know how they react. So we would know how much of the thing we have, we would know what the thing we have is, we'd be able to come up with a balanced chemical equation, and we can figure out what the concentration is. If we're doing an acid-base titration, then we're reacting an acid and a base. We'll learn more about those next chapter, which we'll probably have to get to next week, because I don't feel like canceling lab today. Our net ionic equation, we learned about those last time. It's just the stuff that reacts. For the reaction between hydrochloric acid, just generally an acid, and sodium hydroxide, which is a base, is H+, that's from the acid, reacts with OH-, that's from the base, sodium hydroxide. Those go to react to form water. This is sometimes a helpful net ionic equation to know about. The helpful part, the number of H pluses equals the number of OH minuses. So part of the reason that I was able to very quickly come up with an equation, a balanced chemical equation here, despite not having one, because I know that nitric acid has one H in front, and barium hydroxide has two hydroxides. I know that I need to have an equal number of H pluses and hydroxides. So I saw barium hydroxide has two hydroxides. That means that I need two HNO3s because there's only one hydrogen in front. So I need two of them to get these H pluses to balance out with the OH minuses, which is the important part of an acid-base titration. All right, in our acid-base titration example, we've got an HCl solution. It's represented by this. So we are just showing the H pluses. These get formed when acids dissolve in water, like from HCl. So we can take a solution of acid. This has unknown concentration. So this is the thing we're trying to find the concentration of. And in our burette, we were using burette stands, burette clamps last lab. This is the other thing that they're used for, is these burettes. We've got the base, the OH minus. So we're mixing hydroxide, we're adding it in with our burette. The burette has this little lever on it, this little knob on it that lets us control the amount that we add, the rate that we add it at. And it's also got measurement marks on it, so we can see how much we've added. So we use this, we add drops or a lot of our hydroxide into our solution with our acid. As we do that, we get some reaction happening. We get the OH minus reacting with the H plus to form H2O. And we would also have added to this an indicator. And so that's what we see in this third image of a burette. These are basically 3 frames of a titration. In this third frame, the reason that it's this fuchsia color is because we've added an indicator that lets us know when we've got an excess of base. So we've added a little bit more base than we need, so all of our acid has been neutralized. There's now actually a tiny little bit of excess base, and that causes our indicator to change colors, and that lets us know the reaction is complete. So pink endpoint signals the titration is complete. We've added approximately equal amounts of acid, whatever was in the flask, and base. And since we know the concentration of our base, we know how much of the base we added, we can calculate how much of the acid we had in the solution. We know how much volume we had, or what mass we had, and we can figure that out. Our equivalence point is usually signaled by an indicator. We will be using phenolphthalein, which has a crazy spelling. Phenolphthalein starts with a P. Phenol, and then phthalene, which is spelled exactly how you'd expect. Phenolphthalein. You don't need to know how to spell it. I just like to spell it because it looks crazy. So phenolphthalein is the one that we typically use. It's the one that makes that fuchsia color. That's why I made the slide that fuchsia color. And we have to carefully measure things. So let's take a look-see. Sodium hydroxide is added to an HCl solution. So this is, we would have some acid in here. It's probably going to actually be a weak acid instead of a strong acid. We'll learn about this next chapter. When our sodium hydroxide and their HCl reach stoichiometric proportions, when they are 1 mole of sodium hydroxide for every 1 mole of HCl, they are both completely used up. Everything's just water. Our indicator will turn pink. And for reasons beyond the scope of this class, we need to use a weak base, or weak acid, sorry. Ideally, we end up with this incredibly light pink color. It probably doesn't look pink to you on the screen because it's a little washed out. It's a little bright in here. This dark pink endpoint typically signals that we have gone past our equivalence point. The difference between these two pictures can be half a drop. So there's a little bit of luck involved in getting that perfect light pink endpoint. There's skill, but there's also luck. And the more skill you have, the luckier you get, as it turns out. So an example of an acid-base titration. We want to find mass of calcium hydroxide present in a sample. It's titrated to its equivalence point. Equivalence point is a key word here. This unlocks our ability to use our stoichiometric ratio. The H plus that we added equals the OH minus that we added in terms of their moles, in terms of their number. We added 44.02 milliliters of 0.0885 molar HNO3, and we have a balanced chemical equation, and it's the correct balanced chemical equation. We love to see it. Didn't screw up on this slide, hopefully. So the thing that we're looking for, grams, CaOH2. That would be mass of CaOH2, calcium hydroxide. There are two options for things that we can start with. What's one of those options? Give me a unit and a chemical. There are 3 units on the screen. If you blindly guess, you've got a 66% chance of getting it right. Yeah, 44.02 milliliters. That's what I would choose to start with. Milliliters HNO3. We can't do that fun little milliliters trick here because we don't have milliliters showing up anywhere else. So we're going to need to convert that to liters. Divide by 1,000 to get it to liters of HNO3. In order for us to convert from HNO3 to calcium hydroxide with our balanced chemical equation, we need to be in moles. It has to be in moles. Can't be in anything else. Must be moles. So to get to moles from liters, we've got molarity. If you multiply molarity and liters, as we've seen before, you'll get moles. So I'm going to employ that clever little trick, that fun little trick of converting capital M into moles over liters so that our units cancel out nicely. So this calculation would tell us how many moles of HNO3 we added. And we'll go ahead and evaluate that. The amount of moles that we added, 0.000389577 moles HNO3. How can we turn this into grams calcium hydroxide? There's 2 steps. What's one step we need to do? All right, our next step is stoichiometry. So we're going to do the stoichiometry step. So we look at our balanced chemical equation, 2 HNO3 to 1 calcium hydroxide. We have HNO3. We're trying to go to calcium hydroxide. So we're going to divide by 2. And we would then have moles of calcium hydroxide. Moles calcium hydroxide. Those are the units that are left. And then we get to do a molar mass. The molar mass of calcium hydroxide, 74.092, assuming I didn't screw up or misread something. So our moles of nitric acid divided by 2 times our molar mass, 0.144 grams calcium hydroxide that was in the solution. Another relevant acid-base titration question. What mass of oxalic acid, H2C2O4, is present in a sample if it is titrated to its equivalence point? Again, equivalence point lets us use the stoichiometric ratio. This means that our H plus equals our OH minus. So stoichiometry unlocked. What mass of this acid, oxalic acid, is present if it's titrated to its equivalence point with 18.09 milliliters of 0.2235 molar sodium hydroxide? And again, we're given a balanced chemical equation. So we're given milliliters and molarity. We're asked for mass of oxalic acid. This follows the same solution map as the previous question. So 0.01809 liters because we divided by 1,000 to convert. Liters times molarity, since molarity equals moles over liters. Multiply by 0.235 moles over liters. The liters cancel. So this gives us the moles of H2C2O4 oxalic acid. Then our next step, stoichiometry. We have, that's not the right chemical. This is sodium hydroxide. Our ratio is 1 to 2. So we divide by 2 to switch chemicals. And then we have to multiply by the molar mass of oxalic acid. Which is 90.034 grams per mole. Moles cancel. And we would have present 0.182 grams H2C2O4, which is oxalic acid. Questions, confusions, contusions, perfusions, illusions, delusions? Other illusions? Okay. We're going to talk about some colligative properties that are also relevant for solutions. Our two colligative properties, the two big ones that we're going to start with, are freezing point depression and boiling point elevation. Colligative properties are an interesting type of property because they depend on the number of dissolved solute particles. The identity of the particles doesn't matter. So the identity of the particle isn't important in this case. It just matters the amount that you have. If you add a non-volatile solute, like a salt, to a liquid, it extends the temperature range over which the liquid remains a liquid. If we're expanding our temperature range, I'm going to draw for the 5th time our phases of matter. our lowest temperature phase of matter, solid, our middlest phase of matter, liquid, our highest temperature phase of matter, gas. If we're extending that range, we're bumping up our boiling point. We're bumping down, dropping down our freezing point. So we've got boiling point elevation. It now boils at a higher temperature. And we are decreasing our freezing point. Another name for lowering is depressing. Like a tongue depressor is used to lower your tongue. In the event that you can't just say, ah, and show the doctor your tonsils, right? Freezing point depression. Or your throat or whatever else they're looking at. So this is what we're talking about with boiling point elevation. The boiling point is going up. Freezing point depression, the freezing point is going down. For example, adding salt to ice lowers the melting point. If you've been to the mountains when there's been snow and ice and cold weather conditions, you might have noticed that it's probably just sand on the road, but there could also be salt. If you've lived somewhere where it actually gets cold and snows and freezes, they often salt the roads. The reason that they salt the roads is to take advantage of this freezing point depression. They lower the freezing point of the water, meaning that it's going to be water at lower temperatures. It's not going to be ice, so you're not going to skid out on ice. You'll just be driving over a wet road that's also salty. The sand just adds traction. Adding ethylene glycol, which is a non-volatile solute, to water raises the boiling point and lowers the freezing point, and that's what we would typically call or commonly call antifreeze. It might also be propylene glycol instead of ethylene glycol. The identity doesn't matter. They have similar properties. They're both non-volatile solutes. So the reason that we add stuff to the water that's in your radiator and your engine so that it has a higher boiling point, you're not going to boil over your radiator, and it has a lower freezing point, so your radiator block doesn't freeze in the event that it gets colder than freezing. For freezing point depression and boiling point elevation, the concentration of the solution is usually expressed in molality. Notice that this looks very similar to molarity. We've changed one letter, and now it's molality. It's a different unit. And it's also lowercase. Little m. Minuscule m. Whereas big M was molarity. It also has a different calculation. The top is moles solute. This is the same as with molarity. It's still moles solute. The bottom is different. It's kilograms. And it's solvent, not solution. So in molarity, we had liters of solution on the bottom. In molality, we have kilograms solvent on the bottom. I don't particularly like this unit. The calculations are relatively easy. There's a little bit of a trick sometimes. We'll see shortly why I don't like this unit. I'll show you. I'll demonstrate to you. Okay, so let's say that we want to calculate the molality of a fructose solution containing 50.4 grams fructose, 0.332 kilograms of water. Molality, lowercase m, is moles solute over kilograms solvent. What is our solvent here? Water is our solvent. Water is the majority component. It's also nicely expressed in kilograms. We do not have moles of our solute of fructose. So we'll have to calculate that. 50.4 grams C6H12O6. So we've got 6 carbons, 12 hydrogens, 6 oxygens. Our molar mass is 180.156 grams per mole. So 50.4 divided by that number, 0.279 ... moles C6H12O6. Now we've got everything that we need. We just plug it into our formulae. So divide by our kilogram solvent, 0.332 kgH2O. And it's 0.84, round up to 3, lowercase m, C6H12O6. Now, here's the reason why I don't like it. Capital M, how did we pronounce that? Not what's the name, but like if we have we'll make it a 2M. A 2M solution, how would we pronounce that? A 2 what solution? 2 molar, right? We dropped the itty. The same principle applies to lowercase m. So 0.843 molality, but drop the itty, 0.843 mole fructose. And I don't like it because mole just feels really bad to say. That's it. That's the only reason. I just don't like the way that it comes out of the mouth. Try it. Say mole. Mole. Very fun, right? Anyway, so that's why I don't like it. Now on to the important stuff. Freezing point depression. The freezing point depression of a solution has this equation. Delta TF, the F stands for freezing. So the change in the freezing temperature is equal to the molality times the freezing point depression constant. F again stands for freezing. K stands for constant. So this is the constant of freezing. Different solvents will have different values for Kf. You will always be given the values of Kf on an exam. Other times you might have to go look them up. It's as easy as plugging it into your favorite search engine. The results should come up pretty quick. You'll also be given the equation. All right, so how does this work? We want to calculate the freezing point of an aqueous 1.42 mole sucrose solution. For water, Kf is this nonsense, 1.86 this nonsense. Degrees Celsius kilogram solvent per mole solute. Now the key is that kilogram solvent over mole solute is just inverse molality. So what this actually is, 1.86 degrees Celsius per lowercase m, molality. That's all it is. It's not scary or weird. It's that. All right, so using our delta TF equals lowercase m times K lowercase f sub f. We've been given molality. We've been given Kf. It's as simple as plugging it in. So 1.42 molal times our freezing point depression constant, 1.86 degrees Celsius per mole. So the molalities cancel, 1.42 times 1.86. We get a value of 2.64 after we round for 3 sig figs degrees Celsius. What was the question asking for? Freezing point. What did we find? It's so much more fun when you participate. Is this our answer? What's the normal freezing point of water? It's 0 degrees Celsius. Water freezes at 0 degrees Celsius. What's the name of the principle that we're applying here? What's the name of the idea? Freezing point depression. That means that the freezing point goes down. We calculated not the freezing point, we calculated the change in the freezing point. We calculated how much it goes down. It goes down 2.64 degrees Celsius. This is not our freezing point, this is the change. And so it's actually, our answer is actually minus 2.64 degrees Celsius. It's 0 degrees Celsius minus 2.64 degrees Celsius to give us a lowered value of negative 2.64 degrees Celsius. That's the only thing that's difficult about doing these problems. Literally, in my opinion, that's the only thing that's difficult. The rest of it's really easy. We've done stuff that's harder than that all the time. You need to remember this is the amount that the freezing point is going down. It is not the new freezing point because that would be freezing point elevation. That's not a thing. All right, boiling point elevation. Boiling point elevation is a thing. The boiling point of a solution contains a non-volatile solute, like salt, like ethylene glycol, like propylene glycol, is higher than the boiling point of the pure solid. So you add something that it's not volatile, it increases the boiling point. So antifreeze works by not only preventing the freezing of the coolant in your engine block if it gets below freezing, it also prevents the boiling of the engine coolant in hot climates. It prevents it from boiling over and from keeps your car from overheating. Who's ready for some deja vu? Here it is. It's so similar to our freezing point depression equation. All that's changed is the subscripts. We now have sub B instead of sub F. B for baby? No, boiling. B for boiling. That's good enough for me. So it's B for boiling instead of F for freezing. Different solvents have different values of Kb. What is the concentration in molality of an aqueous sodium chloride solution with a boiling point of 101.78 degrees Celsius? So we want molality of something that has this boiling point, 101.78 degrees Celsius. We've got an equation, delta TB equals M times K sub B. We are trying to find molality. If we rearrange to solve for molality, molality equals delta TB over K sub B. We were given K sub B. Do we have delta TB? Couple people whispering, yes. The delta means change. How much our boiling point went up. If you plug in this number of 101.78 degrees Celsius, you get the wrong answer. Delta TB is the amount the temperature increased. So what is the normal boiling point of water? Normal boiling point is 100 degrees Celsius. New boiling point, elevated boiling point is 101.78 degrees Celsius. So the amount that it went up is the difference between those two. So 101.78 degrees Celsius minus 100 degrees Celsius equals 1.78 degrees Celsius. That is our delta TB. That's the only hard part about this question, in my opinion. That is where most of you are going to go astray or awry or a sourdough. So we plug in that 1.78 degrees Celsius and the 0.512. Again, this crazy unit is degrees Celsius per mole. The mole flips to the top. I drew somehow a two-headed arrow, but with one stem. Our molality, 1.78 divided by 0.512, 3.48, lowercase m, NaCl. If you did it without subtracting the 100, you would have gotten the wrong answer of 199 molal, which would mean 199 moles of NaCl per 1 kilogram H2O. So in 1 liter of water, you have somehow fit 199 moles of sodium chloride, which is 11,600 grams. So 12 kilograms of salt in 1 liter of water. So if we think about it a little bit, we would hopefully be able to catch, hey, that's a little too much salt. The last little bit of property that we're going to talk about is osmosis. Osmosis is also a colligative property. Osmosis describes the flow of solvent, liquid, from a less concentrated solution to a more concentrated solution. The goal of osmosis is moving water or liquid to get equal concentrations. This is the end, the target, the goal of osmosis. So it's moving from a low concentration solution to a high concentration solution. It's diluting the high concentration solution so that it comes down to match the low concentration solution. That's one way to think of it. Water can go through semi-permeable membranes. We have them in our body. it's going to flow from less concentrated to more concentrated. So we've got an example of an initial state that's 0.1 molar and 1 molar solutions. The water is going to flow from this 0.1 molar side to the 1 molar side until the solutions are equal in size. The probably actual mechanistic reason for why this happens is there's ion-dipole interactions. So there's going to be stuff dissolved. It's not necessarily ion-dipole, but there's going to be stuff dissolved in this 1 molar solution. A lot of stuff, the water is going to be attracted to that stuff. It'll move over to that side. It'll kind of get stuck on the things that it's got dissolved, and it's not going to move over to this other side. More interactions with all this stuff that's over here. And that'll happen until it either can't rise anymore because the pressure of this water column is too strong, too high, and it would force it through. Reverse osmosis is the opposite of this process. So they take something that's concentrated, some water that's got stuff in it, and they just push on it really hard and force it through a semi-permeable membrane that only water can go through. And now you've got pure drinking water. That's how reverse osmosis works. Osmotic pressure is also a colligative property. It depends only on the concentration. We don't really do calculations with osmotic pressure. Here's an application. Here's what some instances might look like. Let's take red blood cells as an example. Normally, red blood cells look kind of like a donut, but they don't have a hole in the middle. They just kind of deflate in the middle, kind of like a donut peach. If you put them in an isotonic solution, iso meaning same, and tonic meaning like strength or concentration. So it's the same concentration in the cell versus out of the cell. Nothing's going to happen. The blood cells will be happy. If it's hypotonic, that means you've got low, surrounding fluid is lower in solute concentration. Since it's lower concentration, it's going to flow, water is going to flow into the blood cells. If that happens too much, the blood cells pop. If it's a hypertonic solution, that means it's higher concentration. That will pull water out of the blood cells, which will cause them to deflate. And they don't look quite as evil here as the slides used to, but they do look kind of evil, kind of like viruses depicted in movies, or like whatever the black thing is in the Spider-Man universe, Venom or whatever. So that's hypertonic. This is part of the reason why when you get an IV, if you go to the hospital, they don't just pump straight water into you, because if they just put water into you, it would dilute all the salts in your system. That's bad. It would also cause your blood cells probably to pop, which is really bad. So they put in a salt solution that's what your body is supposed to have, and then that has the benefits of getting you closer to where you're supposed to be in terms of your dissolved salts, and also it doesn't pop your red blood cells. Any questions? Great, we'll stop there.